Hello, welcome to my talk about hair simulation, a project that we did started a couple of months ago. To replace the current hair simulation in Blender. So, just a little bit about me. Does it work? Sorry. Doesn't seem to be. There we go. So I've been a Blender contributor since about 2011-ish. That's at least the oldest Blender conference T-shirt I still own. My first real involvement with Blender development was during the Cosmos Laundromat project in about 2014-15. Where I worked on hair simulation, the particle system, a bit of the color tornado that you see in the title picture, and a bunch of other things. After that, I went to Microsoft for a couple of years, working on the HoloLens and the mixed reality toolkit, and then I got fed up and moved back to Blender. And since 2023, I'm back at the Blender Institute, working on a bunch of projects. So over the years, some of the bigger projects that I've been working on were, of course, the particle system and the hair system. Then Python nodes was a pretty big project for me. On the lower left side here, you see the animation nodes by Jacques Lucke. That was based on the Python nodes. And then, of course, the successor to that was geometry nodes, which is also a big part of the grease pencil transition from grease pencil 2 to 3 that I've been working on in 2024. And I learned a bunch of interesting things during this project, including how to work with curves, how to work with data-oriented designs in Blender, multi-threading, geometry nodes integration, and all that. And this became very handy then during the hair simulation project that we started about half a year ago. So why do we want to do new hair simulation in the first place? So this is a bunch of shots from the Cosmos Laundromat project. The hair simulation is amazing, which is mostly due to the hard work of all the artists involved. It took us a long time to get to this result. So, yeah, you might be thinking, okay, the hair simulation is fine, but there's just a lot of invisible work that went into this. The old hair system is unfortunately at the end of its life. We have a new system in geometry nodes now that works a lot better, and this is what we want to base our future modular design on, so we can do not just hair simulation, but also rigid body simulations and all kinds of other simulation systems that we want to build on this system in the future. The old particle system has a lot of features, but they are in maintenance mode only for about 10 years now. The left side here is a screenshot from Blender 2.75, and the right side is current main Blender 5.0, and it has virtually not changed. So that is one of the reasons we want to replace the system. It's just incredibly difficult to modify and improve on. Because it is mostly spaghetti code, that means it has a lot of interdependencies. If you want to change part of this particle system, it's almost impossible to not break something else. It's all very complicated data design. When you have the particles and you want to make a hair simulation, particles first become curves by growing out of the mesh. That's literally how they are defined. These curves are then converted into a mesh, and then this mesh is interpreted as a hair simulation, a cloth simulation actually, and then the cloth simulation gets transferred back to the curves and to the particles. And all of these data designs exist at the same time, which makes it really difficult to know what you're working on at any given time. And there are some inherent problems with the cloth simulation because it becomes unstable when you just simulate edge meshes without faces. In particular, you can't capture twist energy in these edge curves, and that means you sometimes can add or remove energy numerically in a very unphysical way. So yeah, for all these reasons, we want to move away from the current particle system and re-implement hair simulation in geometry nodes, where we have modularity by design already built in because it's all based on nodes. We have the simulation zone now, which allows us to actually do iterations, which wasn't initially possible in geometry nodes. It was just designed as a modifier. But now we have the simulation zone, and people have already done some quite interesting things with it. So here's like a particle simulation. We have a distance-based effect that spreads out iteratively through these particles. The right thing is a cloth simulation, a very early experiment that I did, based on the same solver principles that I'm using for hair sim now. We also have in Blender now the new hair curves, which are a modernization of the data structures that will form the basis of our new hair simulation. And these curves have full integration in geometry nodes. So they can be freely combined with all the other features that exist in geometry nodes already. And they have attribute supports, which is very important for simulations because it allows us to move simulation data around without having bespoke data structures that we need for the particle systems right now. So that is one of the reasons the particle systems are so interdependent and difficult to work with. All right. In the new hair curves, this is one of the examples that we currently have as a Blender demo. The hairstyles by Daniel Bystedt from, I think it's about 2 years old now. These all are modeled as static hairstyles. And one of the things I wanted to test is, okay, can I add a simulation to this? Can I just take these things, add my own simulation, and just make it work? The answer is yes, I can, with some caveats here. So there should be an asterisk here. There are some obvious issues here if you look closely. A bunch of noise, the hair explodes a little bit, moves not quite right, but I'll explain what these are later on and what we intend to do about these issues, right? So before I go there, I want to talk a bit about what actually is a hair solver, just to give a basic bit of theory. So a hair solver describes a physical system, obviously, and the physical system is made up of constraints, which are just equations that keep certain properties of the system constant. The solver is responsible for satisfying all of these constraints simultaneously, which is what makes it challenging. And then you have to actually write to the positions and the rotations if the geometry has rotations, or the velocity. So both of these can be involved in constraints. And then you do the whole thing iteratively to solve the entire system. The specific physical model we're working with is these Cosmos rods, which are an optimization for thin rods, meaning they can be described entirely by the positions of the center line, and you don't need to actually model the whole volume of these rods. You also need a rotation attribute to capture this twist energy that I mentioned, which is the reason why you can't just use a cloth simulation. And one of the axes of this rotation has to be aligned with the forward direction, which is a part of these constraints. So just a quick overview, there are stretch constraints, which means the hair cannot change in length significantly. These can be soft constraints, so if you have hair curves that model a curly hair, then the curls obviously can stretch if the center line is straight. So there has to be some stretchiness, but generally speaking, these constraints remain fairly stiff. This is complemented with the bending constraints. So if you have hair that is quite wiry, then you would have these stiff bending constraints that keep the relative shape of the hair segments. But this can also be pretty soft in general. Dynamic constraints are constraints that would be updated over time. So for example, the root constraint of the hair makes it attached to the head. And as the head moves around and is animated, then these root constraints also have to be updated. And then there are collision constraints that have to be detected every frame. You have to detect the new contact points and move the hair to the surface of the mesh so it stays outside and doesn't penetrate. The solver method that we're using is the extended position-based dynamics solver, which is kind of a standard method that has been around for a while, since around 2015 in the extended version. I think the general idea of position-based dynamics has been much longer since like at least 2011, I think. So this is relatively easy to implement for just position variables. But as soon as you add rotations, it becomes a bit more complicated, because then you have to deal with quaternions, and quaternions have to stay on the unit sphere, and it makes the whole thing a little bit more error-prone, let's say. So here's the general paper that we're working on, that we're working with, that combines the XPPD method with this Cosrad model that I mentioned. And taken together, this is the basis of the description. Okay, so when we started out doing this hair simulation, we said, okay, let's try and just do it all in node groups. So we just have a whole bunch of node groups without adding any C++ code, which turned out a bit too much, because there are aspects of the solver that can't easily be done in node groups alone. So we took a step back and said, okay, let's do the solver itself in C++, just because doing reverse mapping in geometry node groups alone is very inefficient and slow. But everything else is node groups. So this is a high-level overview of the solver step. So in the first, you have some general setup. You generate these constraints, create the rotation attributes, figure out the initial rotations, and so on. Then it goes into a simulation zone. And one of the first things we have to do is actually subdivide the time step, because the time step by default, of course, is like something like 1/24th of a second. And for a physics simulation, that's just too long. It's not very stable. So you usually subdivide this to something more like 60 FPS or 120 FPS. After this, we can then actually do the dynamics of the hair. So usual Newton dynamics, you move the points along the velocity, you rotate the points with the angular velocity and so on. And this is all completely unconstrained here, but it gives us the initial position that we can then use to do things like detecting collisions and updating the animation. So one thing you will notice here is that the block on the lower left side here is not within the simulation zone. And that's because we want this to be editable by users. And for that, we used one of the new features that we have in geometry nodes now, which is the closure. So the idea with the closure, very briefly, is that you can define parts of your node tree outside of where you're actually using it, unlike a classical node group, which is contained within the place where you actually use it. So this allows us to basically have a node group that contains the entire solver, but parts of it is defined by users outside of that node group. Okay, and after all of these dynamic updates, we can then go back in the simulation zone where we do the actual constraint solving. This is on the upper right here. So this is where the heavy lifting of the actual constraint solver is done. And then all of this runs in a repeat zone for the number of substeps we've selected. And then on the lower right side here, all of this is just debugging output, some statistics to tell the user how good is the solver, these kinds of things. Right, so all of this works. Here's a very early test, so you see there's a bunch of features that are missing. The hairs are completely straight. There's no actual bending angles yet. But it works. I'm just playing around with the bending stiffness here, so making it a bit softer, this kind of thing. Right. So the problem with the first prototype is that doing everything in node groups. Sorry, I should go back here. So yeah, the good parts first. The good parts is that it's very easy to prototype in node groups. You can edit everything, so I can give this to users and they can just modify everything out of the box. And there's not much C++ code, so at least in theory, this should be relatively easy to review. But there are a bunch of downsides. So if you want to collaborate on node groups, you have to, it's just very difficult because you can't really do diffing on node groups. You can't compare two node groups to each other and say what the differences are. If you do math in node groups, it tends to get very verbose very quickly. We also have problems still to this point with using assets, because if you import an asset twice, you get duplicates and it becomes a real mess to sort out. There are some solutions on the way with the embedded asset system, but at the time of this prototype, that wasn't available, and we just didn't want to deal with this problem while working on the node system. So those are all problems for coders, of course, mostly, but for prototyping, it just gets in the way. It's also unclear, like, how do you actually do code review on node groups? And finally, then, how do you actually test this? How do you write an automated test for nodes? It's also unclear. Which is, taken together, the reason we started building our second prototype, to avoid all of these low-level node groups. We said, okay, let's put most of it in just a single C++ node. We may have some high-level node groups, but most of it is contained in a single C++ node that does the entire simulation. So that's roughly what that would look like. You have just the simulation node in the middle in a simulation zone. There is some additional solver state in this data socket. The color here is for this dark green represents a bundle, which is also a new concept that we have, where you have structured data in named fields that you can just combine arbitrarily, and you just need a single socket to represent the entire structure. Now, with this prototype, of course, it becomes very simple. So here's a quick screen cap of me building this up from scratch. Just add a few curves, throw in this node, and within a few minutes, I have it all simulating hair. But there is a bit of an issue now because, of course, now it's a black box. So we have the opposite problem. Now nothing is editable anymore. So how do you get users? How do you allow users to actually control the simulation? Something like, how do you control what are the colliders of the simulation, or what is the stiffness of your hair curves, something like that. And the concept that we've come up with to make this possible is the declarative behaviors. So instead of having a node group where you define everything explicitly, you would have these declarative behaviors, or also world components is another term we use for this now. This is a very simple example with a custom gravity. There's some custom forces that I'm adding here, defining the material density, and there are more of these behaviors that I'll show in a minute. You can just throw any of these together in the bundle and the simulation will understand what to do with them. Now, the next problem that we come up with then is then, okay, how do you actually know what features are available in the simulation? So users don't want to read documentation for this, obviously. We don't want to make them do this. So how do we tell users what is available? How do we make these things discoverable? And that's ultimately when we get to prototype number 3, where we redefine this general concept and actually make it into something more usable. So the typed bundles are the solution to this problem that we envision at this moment. A typed bundle has an additional string field here that contains the type. And it has some nice UI usability support, so you can just click on this thing and it tells you all the types that are available. So the first thing here would be a simulated geometry. We call it XPBD geometry at the moment. We'll probably use a better name in the future. You can add forces. These 2 rod constraints after that are specific to hair curves. But there are a bunch of more generic constraints, like for damping or gravity, these kinds of things. When you make a typed bundle, it automatically fills in all those settings that are part of this. So for a geometry, obviously we want a geometry socket, but you also have the mass of each individual point. This is a field then. You would have, for example, optional rotation support, this kind of thing. And there's a sync button on every node when the settings aren't complete, so you can click on this button and it just fills in automatically all of these settings that are part of this specific bundle. And then, some other features. You can nest these bundles inside each other. You can put a bundle inside a bundle inside a bundle, which allows you to build up hierarchical structures of the simulation world. Right, so here's an early test with just generic soft body simulation, so something cloth-like, some ropes, and there's volume constraints that are just based on the surface area. So indirectly it keeps the volume constant, makes some nice bouncy balls there. Another very promising thing we tested was integrating this whole thing with other physics engines, so Bullet, which we have in Blender right now, but also the Jolt physics engine, which is another rigid body engine that we're looking at to replace Bullet in the future. Box2D was another test just for fun because it's simple and nice. And all of these engines just work with the same declarative behavior bundles that we have for our soft body solver. One thing that we also tested was combining these physics engines with our soft body solver to use the collision that we have in Jolt to then define contacts for the soft body solver. So this is very promising because our collision is very basic at the moment, and we just want to have better collision detection, and Jolt would give us this out of the box without implementing a lot of things in Blender that we don't have right now. So what's the current state of the hair simulation? I showed you this animation here, and I want to point out a few of the issues here that are kind of more or less obvious, and tell you where they're coming from and what we want to do about them. So first of all, these demo files were not made for animation or simulation, which is where some of the issues come from. So some of the hairs just start moving immediately when you add a simulation to them because they are not in a stable rest pose. So a long hair that is just draped over the head will just start falling down naturally. That's expected. Some of the hairs here, especially in the long hair in the second example, start flying out immediately when the simulation starts, and that's because the points of the hair are actually intersecting with the collider initially, just because the grooming tools don't actually take care of that very well, so that there's no strict requirement that they would have to stay out of the mesh, and that makes them get pushed out of the mesh initially and then they gain velocity. So that's something expected that the tools should ultimately prevent from happening. The collisions are also quite basic, so it's probably a bit hard to see, but there is a little bit of jittering here because the contact points get added and removed and move around a lot. So in certain situations, it becomes a bit unstable. Also, like, for example, the hair resting on the nose there is kind of obvious. The interpolation assets, so the assets that actually generate the rendered hairs, they need some work, in particular because when you generate these rendered hairs every frame, it becomes very expensive and also a bit unstable. And then, very importantly, also hair self-collision is completely missing here, so that's a feature that we're going to add later on. But what this would add is essentially some volume to the hair so that it doesn't just collapse into a single sheet. So one thing I had to do here is make the hair much stiffer than it should ultimately be, to compensate for this lack of self-collision, and that shouldn't be necessary in the future. Also the hair like moving against each other, you can see this in this two-colored left example with the cyberpunk hair. It just moves in a very unnatural way. There's no friction between the hairs. I mentioned the issues with procedural hair. You can see here, as soon as the mesh stretches, it generates and removes hairs if they are resampled every frame. So that's something we don't want to happen. And the solution to this would be to split the generating of these hairs into two stages. So you generate the hair once in the beginning, and then you just transfer the movement of the guide hairs to the rendered hairs after that. And that's something we've done here, but it's not part of the official assets yet. What's the stability like? So what you see here is a blooper reel. All of these issues have been fixed, but it's just, there are so many problems that come up during development with rotations in particular. It's just, and there's a lot of work. But all of these issues have been fixed in the meantime. Fun times, yeah. Whee. Okay. Some more things that we probably would benefit from. Visualization as a general term. So, like giving feedback to users about what the solver is doing is something that I want to work on. Visualizing forces internal to the solver, which would avoid some of the problems we had during Cosmos Laundromat, where people would crank up constraint stiffness to very high levels to get control over the solver. But what that was leading to was just a completely over-constrained system that would become unstable very quickly. And it's something that we could have avoided by having better visualization for all of these invisible things that are happening in the solver that artists just cannot see. So that's generally something I want to work on. Performance of the XBBD solver is actually quite decent for the initial version, at least completely sufficient. The parts that are slowest are, I would say, collision detection, which is not really part of the constraint solver itself. But in the future, we might also look at more improved solver versions. So like vertex block descent is a method that is conceptually similar to the XBBD method, but promises to offer much better performance. I'm just throwing these terms out here for reference in the future. And then global solvers are another possibility to look into. They work in a somewhat different way, and they have their own issues, but it's something that we might be looking into. One thing that is currently also missing in Blender is animation for curves in general, armature deformation. We have some experimental branches for supporting this and some new nodes in geometry nodes, but as of right now, artists usually have to do something like generating ribbons, mesh ribbons from the curves and then transferring and then animating these ribbon meshes and then transferring the motion back to the original curves, which is very involved, and it basically requires 3 different objects for the same character. So if we can avoid that, it would make the future of simulation and animation of guide hairs a lot easier. So the design for behaviors I mentioned will be finalized after the BConf. We have a workshop, and then we hopefully come up with a good solution that we can actually give to artists. Collision, as I said, is very basic, and it really only works for rigid and for convex colliders. There are some alternatives. I mentioned jolt shapes could be used for finding contacts in the future. We have some initial tests for this. But it's unclear when or how that would look like. And yet another alternative would be scientists' fields, which have the advantage that they are very fast compared to finding contacts in bounding volume hierarchies or KD trees. They tend to lose some finer detail in colliders, so if you have very sharp edges or something like that. But the speed advantage is very significant. So all of these methods are potential solutions for future collision. Self-collision for hair, I mentioned, can be done with direct to curve-to-curve collisions, which is not something you probably want to do for hair because it's just generating too many contact points and becomes very slow. But there are alternatives which we want to implement, some material point light methods. The basic idea is you convert particle points to a grid, and the density then generates pressure forces on these hair points and also adds friction to give the hair some volume and to avoid sliding of hair curves against each other. So this is something we have to look into. And then last but not least, the hair rest shape is something I started working on before the conference. Is not done yet. But what this would do is avoid sagging of the hair at the beginning of a simulation, which is a very typical effect because artists are modeling hair with gravity in mind, so everything looks as if gravity is already acting on the hair, and then you add a simulation on top of it, and it just tends to sag together, and that's not something you want. So artists, to avoid this, an artist would have to model every character as an astronaut with like hair standing off the head. And that's not something you can realistically expect, of course. So we need this reverse solver that gives us the force-free rest shape. And here's the paper I mentioned there that we will base this on. Okay, and I think that's it. Thank you very much. So yeah, I think we have some time for questions and answers. So yeah.
I have a question about the solver itself, because as you mentioned, we can edit the values of the hair, but can we edit the values of the solver like accessing the substeps, the velocity?
So yeah, the question is, can we change the values of the solvers, like substeps? Yes, of course we can. It's all node-based, so these are parameters of the node, and you can, if you want to wrap this into a more manageable node group, for example, you can expose these as parameters of the node group. Yeah. Yeah.
I have a question. For example, I do like a nice simulation of like a braid. Can I convert it into the hair card for the game development?
Can you do hair cards for game developments? I don't see why not. I don't have much personal experience with hair cards, but I guess for games you might want to simplify maybe the simulation a bit. But yeah, generally.
It's like the whole pipeline is like you making all these cards and make it like by your hands. But is it possible to convert groups to the geometry quickly with ready UVs?
I would say so, yeah, but I'm not sure. But I don't see a problem there. Yeah. Yeah.
Is there a way to maybe have the simulation running while you work on the hair?
That's an interesting question. So, is it possible to change the simulation, to have the simulation running while you're working on the hair, while you're editing hair? So, yeah, basically it becomes challenging when you change the topology of the hair, because then you are adding new points that are not necessarily initialized, and the internal solver state may not match up, and then it would basically detect that and just remove the solver state and start out at, say, 0 velocity. So I think if you're just doing something like repositioning hair, that should be possible, or like maybe subdividing hair, then you just redistribute the properties of the physical solver state. But yeah, if you add new hairs, it might get a little bit funky. Yeah? Sorry, I don't know who was first.
I have a question. This hair solver, if there will be like more different solvers, how they will be interacting with each other?
So,
Is it
yeah.
planned to develop it, like interaction between hair simulation and liquid simulation?
Yeah, so interaction between hair simulation and other solvers, I imagine like fluids, or I showed you the rigid body interaction. As soon as as long as things go one way, it's relatively straightforward. You basically run the solver on like one simulation, and then the results of that are used as inputs for the next simulation stage. So you can kind of layer these things on top of each other. If you need a solver that can do both things at the same time, it gets a bit more complicated. There is support for soft bodies in Jolt, so if you wanted to do something like rigid bodies and hairs actually interacting, you could probably do that in Jolt. I think Jolt is also getting support for Cosmos rods, so that might be a bit of redundancy there. But yeah. I don't know about hair and fluids yet. We haven't really planned that far ahead. So, yeah. Yeah.
Yes.
Front row.
You mentioned performance as a consideration.
Yeah.
In the cyberpunk haircuts, saw some of the hairs following each other. Is that something that is to increase the visual density but still be simulating less hairs?
Basically, yes. We generate relatively few guide hairs. I'm not sure if I have a screenshot of here, but and then we put like, I don't know, something like 20 to 50 or so, I would say, rendered hairs that just follow these guide curves. And for straight hair, you really want to interpolate the guide curves, which we're not really doing here. That's why it looks a little bit funky. Yeah. That's a performance thing, yes. I think the solver itself could probably handle more than just these guide curves. So the thing that is really slow at the moment is collision detection. That's much slower than the actual constraint solver. Yeah? So.
Will the current simulation modifiers be kept as a legacy, or will they be entirely replaced by the new system?
will the current simulation modifiers be kept as a legacy? As long as the particle system is around, they'll just be there. It doesn't cost us that much to keep them around. Eventually, of course, we hope to be able to just remove the particle system at some point because it's a little bit of maintenance overhead. But yeah, with the current feature set, it's not that much of an issue to just keep it around for the time being. So, yeah.
Do you have a vision for how the solver would use data from outside of geonodes that's not just geometry? For example, force field objects or like seeing gravity. How to bring that in?
So, how would the solver use external data like force field objects and seeing gravity? We have some experiments. Jacques tried this out. Because if you want to currently have an object represent a force field, you have to kind of work around the fact that everything has to be geometry. And that's a little bit stupid. So we have this experimental thing where a bundle can be stored in an object, and then you can just put anything into there that you want and represent a force field that way. We don't really have a good design for this yet, but it's something we're aware of and we want to change.
Is there already a place? I know for development you want to kind of manage the amount of noise in terms of communication and feedback from the community. So is there already a place to like gather artists' impressions and feedback, or is that a future thing that will happen?
Is there a place to gather feedback from artists? There are projects on our project site, projects.blender.org, but we don't really have like a dev talk thread at this point. I'm not sure when we will do that, probably after the conference at some point. So. Yeah. Do we have a target release version? I was somewhat hoping to maybe get something in 5.0, but it's a bit questionable, especially because if we make it an experimental feature, then it won't be visible in the release anyway, and then that makes it pointless. So in 5.1, I hope we have something that we can give users. Yeah.
You mentioned like using a fully node-based system and then also having like a node like written in C. Is there like a significant performance difference between those two nodes?
Is there a significant performance difference between node groups and C++ nodes? It depends. So there are some things where node groups are basically just as fast as C++ nodes. The reason, well, the short answer is it depends. So I initially implemented the whole thing with node groups, and it kind of worked. There were some critical parts like mapping from one geometry to another, or basically doing a reverse mapping. That was kind of tricky to do with just node groups, and I basically had to make like a giant point cloud that represented like all the different combinations, and then reduce that again. So that was just a lot of overhead for something that should be a lot simpler. So most things are just as fast in node groups. Yeah. Again.
I had one more question, sorry. Is it going to be possible to maybe like outside of the basic mapping to map a rig to a simulation?
Is it possible to map a rig to a simulation?
It's like if there's maybe some consideration to do something like Rigify for the hair.
Right, something like Rigify for hair. So we don't currently have support for armatures in geometry nodes. There are some work in progress patches to get bone information, and I did a few experiments myself to just have a node that does the armature deformation for any geometry you put into it. So the need is there, and there will be something, and then we can basically, Well, that's just the deformation side, obviously. So if you want to actually construct an armature in geometry nodes, I don't think we have a plan for that right now. Yeah. Yeah.
Speaking of armatures, there has been talk about adding like guided simulations for animated hair in Blender, and how would this particular setup of node groups work with guided simulations for animation?
So how would this setup work for guided simulation? Sorry, can you explain what this?
How would this node group setup work with the guided simulations which are hand animated for characters?
Right. So hand animated character animation. So I assume that would mean actually animating the hair, the guide hair, right? So yeah, we've discussed this a little bit. There are different ways in which you can mix animation and simulation. So one of the easier ways to do this would be to just split your guide hairs into two groups, like one is animated, one is simulated. So you could have like most of the hair animated and then have some simulated loose hair that flies around that to give a bit more realism, something like that. If you want to use animation as a base layer, I think that becomes a little bit more complicated because then you have to define how the simulation reacts to that. I don't really have a good answer to that. So if somebody has experience with this, I would love to hear from you. Yeah. Anybody else? Okay. I don't see any hands then. Thank you.